Here we're going to talk about machines, and what machines are devices that can either multiply forces or change the direction of the forces. And by multiplying forces, it means that a machine will help you do something that you couldn't do otherwise, like something that would take 50 newtons, but you couldn't do 50 newtons, you could do with 10 newtons. Or to change the direction of the force. If the force is acting in that direction, you could change it to make it go in another direction. Now, an important thing about machines is that they can't create energy at all, but they can transform energy from one form to another, because it's not possible for them to create energy out of nothing. But they can turn it from one form to another, like from kinetic to potential, or they can transfer it from one location to another. So that means they can't multiply work or energy. What can machines do if they can't multiply work or energy? What can they do?
They can transfer it.
They can transfer energy. What else can they do? What can they multiply?
Work times time.
Not work times time. Just looking up here, what could they multiply?
Forces.
Yeah, they can multiply forces. Okay, so this is the principle of a machine, that the work input equals the work output. So you put some work into the machine, and then the machine does some work. And the way you can multiply forces is, what happens is your input force times your input distance equals your output force times your output distance. So that's an equation that you need to know. So that equation, did you want to write it down? Okay, so the reason why this formula works is we're saying with a machine that your work input equals your work output. And work is force times distance. And so the force that you input times the distance that it acts over equals the force that's output by the machine times the distance that the machine acts. So if you look here, this is an example. It's a very simple machine. It's a lever. And so with a lever, you have a point of support called a fulcrum. So right here we have a fulcrum. And the lever rotates on that fulcrum. And it allows a small force here. So if you look here, you push down with a small force, but you do that over a large distance. Then that means your output force will be big over a short distance. So when you look at your input, this is your input. Usually what you'll see with input is small force, big distance. And your output will be big force, small distance, because your goal is to be able to produce a big force from a small force. So usually your input force is smaller than your output force. Okay, so here's another example of a machine. This machine, the pulley, what it does is it operates like a lever, except the fulcrum is right here. There's the fulcrum. And what the pulley does is it changes the direction of the force. So the woman here is pulling down, but then the force on the other side is pulling it up. So this particular pulley, this class 1 pulley, just changes the direction of the force. But you can also set up pulleys that allow you to decrease the input force. So if you look at this picture right here, the woman is pulling on this pulley, but the pulley has 2 ropes attached to it. So each rope is providing a force. And so your output force is going to be twice as much as the input force that the woman is applying. So this is an example of multiplying a force. And so here, because it's attached in 2 places, the input force is half as much as the output force. And then if you think about it, as she's moving it, she's only going to move it half the distance because the rope is wrapped around it.
Mm-hmm.
Okay, so let's take a look at this problem. In an ideal pulley system, so this is just like our first example, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 newtons. For every 1 meter length of rope she pulls downward. Okay, so no, this is not like our first example. This is just a pulley system. It could be any kind of pulley system. So in an ideal pulley system, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 newtons. For every 1 meter length of rope she pulls downward, how does the crate rise? So she is applying a force of 25 newtons. And the crate.
C.
So C. And how did you get C?
Because the force applied has to be the force that's exerted.
The work input has to equal the work output.
Right.
So the 25 newtons times 1 meter. So that's the force input, and the input distance is 25. And then the output work is 100 newtons times 25 centimeters, which is a quarter of a meter, which is 25. So that's why it's the same. Okay, so now we'll talk about efficiency. Efficiency is the percentage of work put into a machine that is converted into useful work output. So here we have an equation. The efficiency equals total energy output over total energy input. So that is a formula you should know. So you might want to write that down. Okay, so even though we said that work input has to equal work output, that doesn't mean that our energy input really equals our energy output, because every machine has some efficiency, some percentage. It's some percentage of the energy input that you can get as useful energy output, and no machine can be 100% efficient. So let's say we have a certain machine is 30% efficient. This means that the machine will convert, so it's 30% efficient. Will it convert 30% of the energy to useful work? 70% of the energy input will be wasted? Or 70% of the energy input to useful work and 30% will be wasted? Both of the above or none of the above?
A.
Yeah, it's going to be A, because it's 30% efficient, so 30% of the energy will be put to useful work. Okay, now we'll talk about recycled energy. So this is when you re-employ energy that otherwise would be wasted. So, for example, when you have a power plant and you're producing electricity, you also, as a byproduct, produce heat. So that would be wasted energy, but Edison used that heat to heat his building, so that's recycling energy. So typical power plants waste about 30% of their energy to heat, because they are built away from buildings and other places that use heat. So right now, we have the power plants are wasting about 30% of their energy to heat because the heat's not doing anything useful. All living things need energy. Our bodies are machines, so they need energy. And the way they get that energy is by feeding on hydrocarbons, things like sugar, that release energy when they react with oxygen. So really the way we get our energy is just like burning gas in an automobile. We take our hydrocarbons, things like sugar, and react them with oxygen. And when you react with oxygen, that's combustion. And then you get some energy out of that. And so when you have food, there's more energy stored in that food than in the products after metabolism. So saying you start with glucose, that has a certain amount of energy, and when you're done you have carbon dioxide and water, and that has less energy. So the energy that is no longer in the products is energy that your body can use. So what are some sources of energy? The primary source of energy is the sun. So let's think about the ways the sun gives energy. It evaporates water. So the sunlight evaporates the water. The water falls as rain. The rain flows into rivers. Now in the rivers, they can flow through generator turbines, so turbines in the river that turn, and then those turbines can create electricity. And then the water goes back to the sea where it can be evaporated again. So that's one source of energy, is using the sun to evaporate water, which then goes into rivers. You can also directly convert sun into electricity using photovoltaic cells, so like solar panels that you've seen on roofs of houses or on tops of billboards, or even sometimes they have them in big solar farms. Also wind power, the wind ultimately comes from the sun, and so the wind power also turns generator turbines. So here's a picture of photovoltaic cells on rooftops that catch the solar energy and convert it to electricity. So if we think about how much energy comes from the sun, more energy from the sun hits Earth in 1 hour than all the energy consumed by humans in an entire year. So if we could capture 1 hour of the sun's energy, we would have enough energy to power everything that we needed for a year. So, okay, another source of energy is a fuel cell. And a fuel cell runs opposite to the battery that's shown. So in the battery, electricity separates water into hydrogen and oxygen. So that would be using a battery. A fuel cell would be the opposite of that. You take hydrogen and oxygen and compress them at the electrodes, and when you do that, you create an electric current at the electrode. So that's the way a fuel cell works. We also can get energy from concentrated energy sources, such as nuclear power. Nuclear power is stored in elements like uranium and plutonium. And a byproduct is geothermal energy. And geothermal energy is held in underground reservoirs of hot water to provide steam that can drive turbo generators. So we can make nuclear power ourselves, and also geothermal energy comes from the nuclear power that's natural, and underneath the earth you have these reservoirs of hot water that we can tap. So there's geothermal energy that we could tap to drive turbo generators. You also have dry rock geothermal power that's a producer of electricity. You put water into cavities in deep, dry, hot rock. So if you dig down really far, it's very hot. You put water into that. The water turns into steam, and then it reaches a turbine at the surface. And then after exiting the turbine, it's returned back to the cavity for reuse. So what you're using is the heat of the earth to produce steam, and that steam can drive a turbine to make electricity. And that's that.